The most fundamental principles of modern physics predict that the generation of an enormous and complex universe like ours is practically impossible. According to physicist Luc Barnes, there's a 1 in 10 to the power of 136 chance of forming any complex universe where galaxies, stars, and chemistry can exist, with several free parameters needing to take very precise values. Or, as physicist Paul Davies stated, there is absolutely no evidence that the universe should have the set of physical constants it possesses. Can we truly grasp how complex each atom and molecule is? As Paul Davies further states, the molecules in living cells perform a dance of exquisite fidelity, orchestrated with stunning precision. Vastly more elaborate than the most complicated ballet, the dance of life encompasses countless molecular performers and synergetic coordination. Let's look at the nucleus of the simplest atom, hydrogen. Hydrogen is formed by a fundamental particle called an electron, forming an outer shell, and a composite particle called a proton, forming the nucleus. The very finely specific interaction between three particles, called quarks, and the gluon stabilizes the nucleus and allows the formation of larger molecules. Their properties and interactions must be perfectly balanced like a transistor in a chip, otherwise, the atom would be unstable. This is true for most, if not all, particles forming the universe. Indeed, the majority of particles exhibit quite singular and complex interactions with others. Photons, for example, must have specific interactions with quarks, electrons, and other particles to allow the existence of atoms. Otherwise, matter could not exist. Each of these particles can be better represented as local fluctuations of a specific field. At the beginning of the universe, these were the strong, intrinsically random fluctuations of the primitive universe that broke symmetries and generated the particles known today. This can be compared to throwing stones at windows, forming quite complex patterns. Truly random conditions have all chances of producing a universe without matter. But perhaps a future revolutionary theory will show that these seemingly independent events are actually all connected, and thus, not due to chance. This is not a common opinion among cosmologists, but even in this case, even if a new theory could show that the only types of particles that can be created are those we know today, how to explain their distribution in terms of quantity? Indeed, the quantity of certain particles must also be finely adjusted for the existence of a complex universe. The most fundamental principles of quantum physics tell us that the distribution of particles in the universe also depends on stochastic, purely random event. In all models, the conditions of the primitive universe are drastic and far from equilibrium. The improbability is so high that it would be comparable to finding a very particular lineup in a game of billiards or the formation of a beautiful painting by blind ink splatters. This is why physicists are considering the possibility of a multiverse. Perhaps the Big Bang that generated our universe was just one among an enormous, perhaps infinite, number of other Big Bangs. Or perhaps we are in a universe with multiple local variations, as in some inflationary theories. However, different theories that account for multiverses have not truly managed to eliminate the problem of free parameters. Within the framework of these theories, our universe remains just as improbable. As one of the greatest cosmologists of our time, George Ellis said,
"It seems quite safe to say that no new theory, however revolutionary, will make all these improbabilities vanish. The realization of the complexity of the universe makes it difficult not to use the word miraculous without taking a position on the ontological status of the word."
So, how could random events produce exactly the right outcome so many times, resulting in such a vast and complex universe?